Today, we're going dark. We are going to deconstruct one of the internet's most powerful and, frankly, bluntest weapons of disruption, the distributed denial of service attack. This isn't about being sneaky. It's about pure, overwhelming force.
You know, at the very heart of every single digital service we rely on is a system with finite resources. Every server, every app, it has a breaking point. And this simple, fundamental truth, that's the vulnerability we're about to see exploited on a massive, massive scale.
So, what exactly is a DDoS attack? Well, think of it as brute force cranked up to 11. This isn't about stealing your data or hacking into a system. Nope. The goal is pure chaos, to make a service completely unusable by drowning it in a tidal wave of garbage requests. To really understand the attack, you have to understand the target first. Every server out there is operating within a very strict set of limits, and it's so important to realize these aren't bugs or mistakes. They're the physical and logical constraints of the system itself, and they are the exact vulnerabilities an attacker is about to go after. Okay, first up, network bandwidth. The easiest way to think about this is like the highway leading to a city. It can only handle so many cars at once. If you create a massive traffic jam that clogs every single lane, well, nothing gets in or out. It's the most basic bottleneck there is. Then you have TCP connections. Imagine the server is like an old-school telephone switchboard. Every time a user connects, an operator plugs in a cord to open a line for that conversation. But what happens when you have a limited number of lines, and every single one is tied up? No new calls can get through. Period. And then, of course, there's the server's brain, its CPU. Every single request you make requires some amount of processing power, but a CPU only has so many cycles it can perform per second. So if you just bombard it with really complex tasks, the whole system doesn't just slow down, it grinds to a dead stop. And finally, there's memory, or RAM. This is basically the server's short-term workspace. Every active user, every process, it needs a little piece of that workspace to function. So what happens when you fill that entire workspace up with junk? The server can't think, it can't process anything new, and critical systems just start to fail. All right, so we've laid out the vulnerabilities. We know the weak spots. Now, let's look at the weapon that's purpose-built to exploit them. The real power of a DDoS attack isn't how clever it is, it's the scale, a massive coordinated swarm. We are talking about botnets, literal armies of infected devices. You might have heard of the infamous Mirai botnet. It was built from everyday things like security cameras and home routers. An attacker can control hundreds of thousands, sometimes even millions, of these so-called bots from all over the planet. And the command structure is just brutally simple. First, a bunch of devices get infected with malware. Then, a central command and control server, or C2 server, issues a single order, attack. And just like that, an army of bots instantly starts blasting the target with traffic. A coordinated flood from every corner of the globe. So what happens when this massive, coordinated force slams into a system with very finite limits? Well, you get a cascading failure. Let's watch this collapse happen step by step as each and every resource gets pushed way past its breaking point. The attack begins, and the very first system to feel the pressure is almost always the most obvious one, the network connection itself. This is where the floodwaters first hit the shore. This is a pure volumetric attack. The goal here is simple. Try to force, say, 100 gigabits per second of traffic through a pipe that was only built to handle 1. The pipe doesn't just get slow, it becomes completely and utterly saturated. There's literally no more room. And here's the devastating consequence. Once that network is saturated, it doesn't matter how fast or powerful the server behind it is, legitimate requests from your actual users can't even get to the front door. As far as they're concerned, your service is completely offline. But okay, let's say some of the attack traffic manages to squeak through. Well, the server's ability to even manage connections becomes the next target in line. This is where things get a little more clever. In what's called a SYN flood, all those bots initiate a connection. They basically say hello to the server, but then they never complete the handshake. So the server, trying to be polite, holds a connection slot open for each one, waiting for a reply that's never going to come until every single slot is filled by these ghosts. And the result? The connection table is full. A real user who tries to connect now just gets a busy signal. The server physically cannot accept any new conversations. It's completely locked up. And finally, if all that wasn't enough, attackers can target the very heart of the server, its ability to think and to remember. And this is where the attacks can get really stealthy. So we've seen volumetric attacks, which just hammer the bandwidth, and protocol attacks, which go after those connection tables. But application layer attacks, they're different. They use what look like legitimate requests, like asking for a really complex search on a website, to force the server to do a ton of expensive work. This can max out its CPU and memory with just a fraction of the traffic, which makes these attacks incredibly hard to spot.
So, how in the world do you fight a flood? You can't just block one drop of rain. You need an entire system of defenses, a digital immune response, really, that's designed to absorb the hit, filter out the bad stuff, and deflect the attack.
Yeah, the modern defensive toolkit has a lot of layers. You've got rate limiting, which puts a cap on requests, load balancers to spread the traffic out, and then there are these massive global networks that use cool tech like Anycast, which cleverly routes all the incoming traffic to the nearest data center. This distributes the attack across the whole planet, so no single point gets overwhelmed. It's all about absorbing the flood before it can ever reach your actual server.
Here's a perfect example of that in action. On the left, you see a server just buckling under a SYN flood. But over on the right, a web application firewall, or a WAF, is sitting out in front. It sees the malicious pattern, identifies it, and just drops the attack packets right then and there. The server behind it stays completely healthy, totally unaware that a storm was even raging.
You know, surviving a DDoS attack isn't just about having the right tools. It actually demands a fundamental shift in how you think. It's all about designing your systems with the core assumption that the internet is, by its very nature, a hostile environment.
And this gets to the core reason why DDoS is so brutally effective: the asymmetry. It is incredibly cheap for an attacker to rent a botnet and launch an attack, but it is incredibly expensive for the defender to build and maintain the global infrastructure needed to withstand it. This economic imbalance is the real battlefield.
So what's the big lesson here for anyone building things? It's really a shift in thinking. You have to design for the worst-case traffic, not the average day. You have to assume every single request coming from a client could be malicious. You need to build systems that can shed load and degrade gracefully when they're under pressure. And most importantly, you have to identify and aggressively protect the parts of your application that are the most computationally expensive to run.
And that really leaves us with this final, critical question. In a world where we know absolute security is pretty much an illusion, the goal can't be to build an unbreakable fortress. The real challenge is this: how do we design systems that can bend without breaking, that can absorb damage and recover gracefully? That, right there, is the true essence of engineering for resilience.